means I need to get my stuff together.
Okay, let's begin. So let's go back to where we were last time. Discuss it a little bit more, see what's going on. It's not just a calculation. We're going to use all this for something eventually. So we were discussing this problem right here where you have some xi's, a collection of IID realizations from a normal distribution. I'll say you know sigma squared. Generally, you have no idea. So you have to estimate that. It's a little fictitious. I could imagine cases where you're running some precision instrument and you know the tolerances of the instrument, and you know how to check if that instrument is in spec. I see scientists do these sort of things, and sometimes they know what sigma squared is, or the resolution of something. So maybe this is an analysis like that. But really, we're going to need to estimate the variance eventually, and so we'll do that next. And I'll show you how to do that. And I'll show you another contrived case where mu is known and we estimate the variance. Okay, you might say, what good is all this? Just shows how to do the real thing. You will use both of these calculations in the future. So when I tell you about Gibbs sampling, you're going to be using these conditioned distributions iteratively. So all of this is worth something in the end, and I think we can learn something about analyses as we build these up in their conditional ways. So let's finish with this discussion of trying to learn the conditional distribution of mu given x bar. And I might say, hey, be real specific about this. Tell me that you know sigma squared over here. So on the right-hand side of the bar, why don't you explain it to me that you know sigma squared? I'm going to start getting a little bit more reduced in my notation. You can tell with this equation that I know sigma squared because it's an input into this. And so sometimes in the literature, they're not so specific. And so you have to write out the notation a little bit more clearly so that you can do the math and verify everything they're doing is right. If you spot an error, you have a new paper to create. And so sigma squared is in here. And so what we ended up finding under this conjugate prior, right here, where mu naught and sigma naught squared were hyperparameters, I need to specify them that the posterior distribution, what I know after seeing the data, is another normal distribution because it's conjugate. So you can check to see if this is conjugate. They both live in the normal distribution, the prior and the posterior, so whatever prior I use was conjugate. It's the same distribution. I can come up with the conditional the conditioned expectation on the data and variance. And I have notation for those. So the expectation conditioned on x bar. I like to use this notation to tell you that I've learned something from the data and what the data input is. So let me just ask a question real quick. Let's say you did know sigma squared and you had some good idea for mu naught. What might you do about this parameter? How might you specify it?
Infinity.
You can think about it different ways. You can think about it as a weight of how much you value this point right here. If you knew sigma squared, you kind of have a scale on weights. So if I plugged in sigma squared right there, this parameter, the real one, then I'd be saying the prior is contributing one data point's worth of weight. Okay, so that's how much offset the prior is offsetting you. And I could scale that down. I could say, hey, I want it only to be a half data point worth of weight. And so I could divide sigma squared by whatever number I wanted to and kind of multiply it by saying, this is how much weight I want to put on my prior. And people will do that, and you might have subjective reasons to do it. Okay, so there's kind of an idea. Mu naught, how do you specify it? You really need knowledge. That means where you're centering all of this. So some people will come in and they'll look at previous studies. And they'll collect a lot of information from the previous studies. And they'll include all those previous studies as weights and maybe multiply a whole bunch of previous studies as weights with all their own mu naughts in there. Mu naught per study, multiply them all together, and that's my prior. And I decide how much weight to put on each one of those studies. That's a subjective Bayesian analysis. It's called meta-analysis. So I'm using either a database of information to calibrate everything, or I'm using scientific literature. So those are all common practices. course, we ended up discussing what happens if I take this parameter and I blow it out to infinity. Maybe that's so-called objective analysis. Now, anytime you use this word, always be thinking, what do I actually mean by objective? I'm like everybody else, and sometimes I get tired of people's grumbling, and I get impatient. I say, well, it's objective. Leave me alone. I know more math than you. And so, but be mindful when you use the word. It means something, and it's usually a mathematical meaning behind it. And so maybe I'm trying to be not sensitive to my prior choices. So there's a couple different ways that you can think about this prior, that when I blow this thing out to infinity, effectively, the prior becomes this. My prior is essentially pi mu. It's going to be proportional to 1. It's some constant. It's flat. And so that's what's happening to this thing. Now that might really bother you. That it's like, well, what am I doing? I've got my Bayes' theorem, which is prior distribution, which means probability distribution, times likelihood. You want to think about it as sampling distribution, and I'm flipping the conditionals, so be it. Okay, but it is a function of the parameter space, so that is technically a different function. So that's what we call likelihoods. And that concerns probability models, and that's not a probability model. So this is not proper. This might bother you a lot. So this is the language. Proper means this. Proper distribution and this could be an unnormalized distribution. And I'll call that, this distribution, I'll call it F. Okay? And I'll just plug in some dummy argument right here. So I'll call it psi. Okay? None of that's important. It's a probability model on psi, some probability distribution on it. A proper distribution has the property integral f psi d psi is less than infinity. That means it's a number. It's an actual number. I can normalize it, aka it's useful to me. I can turn it into something between 0 and 1. Can't do that, totally not useful for inferences. Bear in mind, we're not doing our inferences off of this. We're doing inferences off of the posterior. So we want to go back and check what the posterior is, and when we take the limit in this solution, we get this. Pi mu given x bar is going to be a normal centered at x bar with variance sigma squared over n. And we might like everything about this distribution. So if you don't like thinking about it as an improper distribution, the correct mathematical way to think about this is a sequencing limit of proper distributions, normals. So I'm getting more and more diffused until I hit this thing. And so that's the measure theoretic way of thinking about this. So it tells us everything's okay. This is a limit of something proper. I didn't use anything that was just some function. I used a limit of proper functions. Now you might say in the limit it's not proper, it still bothers me. And the mathematicians will try to encourage you to think it's okay. Saying that, I'm just going to tell you this is a pretty good answer. Maybe I'm willing to use it. So I'm using this Bayes operating procedure, likelihood times prior, and I'm getting good answers out of it. So maybe that's an engineering way to think about all this. I don't really care about all that. I just want procedures that help me to do the right thing. Maybe I can give you some mathematical assurances along the way. Here's how I think about Bayes, just as a aside. And I'll keep saying this throughout the class. So Bayes is, to me, likelihood. So theta given whatever my data is times prior. And both of these things do something that can be beneficial for me. So this allows me joint inferences. Has joint inferences. Connections with the data. Okay, so maybe theta right here is theta 1, theta 2, so on to theta p. So this is a p-dimensional inference. So I want to understand the relationships of all of these parameters. The likelihood has that information built into it. It has that connection with the data in the same form as what produced the data in the first place. So I should be able to use that scaffolding to try to learn what is the relationship between the data and these parameters. And then the prior does something for me. It regularizes my space. So it has regularization. So what I mean by that is, if you think about our binomial example, I was penalizing the endpoints with that U-shaped thing, and I said that did good things. So I wanted to put a little bit of mass on 0 and 1, so even if I have low sample size and I don't see any zeros, I'm not willing to say that the probability is just vanishingly small. The MLE would be a bad answer. The worst statistical analysis in the world is if I get a vector of like 7 zeros, I end up saying, well, the MLE is 0, and my variance is 0. P times 1 minus P. So P hat times 1 minus P hat. Worst statistical analysis ever. Can't ever happen, it's impossible, is what you would be saying, because we haven't seen it yet. We're supposed to be looking beyond that. And this can help you with that. So penalize your space in just the right ways. And so for me, it's just that functional form, and there's lots of good reasons for using these functional forms right here, but you might think about it as limits of proper distributions. If you're a mathematician, you might think of it as a tool. It measures things, and it has all the right properties. At the end of the day, we have to build these things anyway, and we usually have to choose those. So we usually have kind of an engineering sense on our mind, and not all the limiting sense. But maybe this flat choice is good, because we come up with this answer. So maybe I say I don't need any regularization because there's no boundaries and everything, so I'm going to use the flat prior. I'm also going to think about the nature of the parameter. So recall x bar given mu and sigma squared. This is normally distributed. It has parameter mu, and it has variance sigma squared over n. Okay? That's something that I could figure out about x bar if I knew each of the xi's was normally distributed. When I average them, I keep the same center, and I reduce my variability. That's why we like averages. I could do that by looking at moment generating functions. I could work this out explicitly. I could do a convolutional integral. Lots of ways that you could do this. Transformation of variables. All of those really are synonyms in a lot of ways, but I've got a lot of tools for doing this. I encourage you to practice those things. So if I ever write something down, you go, I wonder why that's true. It's a good homework problem for you. And so remember, we might want this limiting prior. So this is the flat choice. I come up with an answer that looks like this, but in the limit washes out all the mu naughts, sigma naughts. So I come up with this posterior distribution. My posterior pi mu given x bar is going to be normal x bar sigma squared over n. We did a lot of work to do that. Remember what I did is I wrote down the likelihood, I multiplied by the proper prior, then I took the limit of the prior. Let's just shortcut a little bit of this work and rederive this. So just remember, this is proportional to likelihood times prior. So this is going to be proportional to. I'll pick my favorite form of likelihood. Carry too much work with me. I'll write down the normalized version of the sampling distribution. So sigma over root n, e to the minus 1/2 x bar minus mu squared over sigma squared over n. That's the likelihood function. I could have written this down as a big product. It would be proportional to this as well. You can verify that. But This is the likelihood I like to use. I like to invoke, I know things about sufficiency, I know the distribution of X bar, why not just use that? If I go to a computer and I have a big product, I'll expect my computer code not to work very well. If I have something like this, I can expect it probably to be problematic because I have E in there, so I probably need to take some logs if I ever do this thing on a computer, but I only have one thing that's unstable, and I can make it stable. All stuff that if you don't know, you will experience, I promise you. Times the prior. Well, that's pretty easy. I said all this is up to proportionality. Keep in mind this is a distribution on mu, so I might make it look like one. If you'll forgive me for a moment, I'm going to do something. I'm going to take X bar and mu and spin them around, because I don't like to look at normal distributions with the argument on the right-hand side. So why was I able to spin those around? Because I'm squaring it. So I just changed the sign. And it looks like this thing is already normalized for me. Turns out this looks like a normal distribution in mu. And I happen to know that if I integrate this, it would add up to 1. Does anybody know how to integrate over this function? If you were to show that this is the right normalizing constant? Just a basic undergrad question. Do I still remember how to do it?
You knew with polar coordinates?
It's the polar coordinate thing. That's how I know how to do it too, and I don't know any other way to do it. So yeah, you do it all in polar. No surprise, 2 pi jumps out at you. It obviously has something to do with something radial. So anyway, this already did just happen to give me the posterior distribution. I didn't actually have to do any solving of anything. Remember how we did it last time is we expanded the square, recognized the conditional variance, then the conditional expectation by looking at the quadratic term and the -2 linear. But in this case, because I didn't really include prior information, I included prior ignorance. And this might be a really good prior, but let's think about the nature of this parameter mu. What is mu? In the original distribution, it's a shift parameter. So it takes this distribution on X bar. It's got some variance, sigma over root n. The distance to the inflection point, so the standard deviation. And if I take mu, sorry, this is mu down here, mu, and this right here is going to be px bar given mu and sigma. So mu just slides this back and forth. It's a shift parameter. If I move it by 5 units, that distribution moves by 5 units. So it's a linear shift parameter. And so maybe I want a prior that's invariant to shifts. The nature of that parameter is a shift parameter. It shifts. So I want to include prior information that doesn't tell me about the nature of that parameter. I want it invariant to that. So I want to provide information in some objective way, and this turns out to be some form of an objective prior. We'll talk about it later. It's transformation invariant. It's shift invariant for obvious conceptual reasons. We'll talk about scale invariance later, and I'll give you a formal lecture on what's called Haar invariance. You take the nature of that parameter and you make it invariant to that. But this one's pretty easy to conceptualize. And the important thing here is to notice that these two parameters, these two things that come into the model, X bar and mu, you can see them right here, they're symmetric. This prior is symmetric as well, about whatever one you're pivoting around. This is symmetric. And it makes inferences easy. Keep in mind what a Bayesian is trying to do. They're trying to invert the analysis. When it's symmetric, inversion is as easy as working with the original thing. And so in these cases where we've got a shift parameter and it's symmetric with our data, like a normal distribution, a Bayesian and a non-Bayesian tend to agree with each other. And that's what we saw last time. So the intervals that we end up getting out of this, the credible interval is just this, X bar minus 1.96. I'm going to make this the 95% credible interval. Sigma over root n. X bar plus 1.96. Sigma over root n. This is a statement about mu, where we believe mu lives. And specifically, we're making a probability statement about this. It's a 95% credible interval. So credible intervals just soak up 95% intervals, soak up 95% of the mass, and they tell you where 95% lives. Now you could shuffle that around in a lot of different ways. So I could come all the way from the left and add it all up, but that doesn't quite make sense. So it'd be this really long interval. Normal distributions are symmetric, and so I could chop off the tail areas, and that would be equivalent to giving me the highest mass area as well. The shortest interval because of the symmetry of the problem. And so this is a HPD, highest posterior density.
It's only like that in the case of the order, right?
Symmetric distributions. Symmetric distributions, I could just chop off the tails rather than adding up the mass, and they're equivalent to each other. So this is an equitail. So you get both of them out of this because it's normal. Everybody agrees when everything's normal. And so what that means is I looked at my normal distribution. That's this right here. Centered in X bar. Has a distance, sigma over root n, right here. And then I pick this lower limit. I'll call it lower Bayes. And I pick this upper limit, so that this interval would be the shortest interval that collects 95% of the mass. That's all this stuff in here. So this is 2.5%, and this is 2.5%. The symmetry makes this problem very easy. Unlike our binomial beta one where we said, is it HPD? And I said it's really close to HPD, but it's not, because the beta distribution isn't symmetric. And all I did was pull off the 2.5% tails. So I looked at this 2.5% quantile and this 97 one. And those are these numbers right here. So this is lower Bayes, this is upper Bayes. Bayesian interval. And I can interpret this as a probability statement. So this is X bar where it's centered, but this axis represents mu. And the height represents this normal density. And so this is a probability statement about mu living there. So the Bayesian has a totally different conception of what this thing is. This is a probability statement for where mu lives. So let me just write that down. For mu. So the Bayesian's giving you a probability distribution on the unknown stuff. Now the non-Bayesian, we came up with an interval, and a lot of people would agree with this interval, but what we did to construct it was mentally very different. So what we did is we made a probability statement about X bar. So for the non-Bayesian. What we do is we make a probability statement about a statistic. Now there's optimal ways for doing this. So the probability of X bar, this is our probability statement, it's about X bar. And I can say it lives between mu minus 1.96 sigma over root n and mu plus 1.96 sigma over root n. And I can say that's 0.95. This is what's random.
So it's symmetric with respect to the base.
It's just because of the symmetry that we get the same answer. And so what a non-Bayesian's going to do now is they're going to pivot and shuffle this thing into the bounds. Okay, so pivot. You don't really change anything. This is a pivotal quantity. There's properties of those. If you take an inference class, they'll tell you how to construct this. Turns out this is a really good choice for this. It has sufficient information about mu. It's got all the stuff you need to know. So Bayesian didn't quite know all that. It just took likelihood times prior and came up with a cool conditional answer. Pivot, you end up just rearranging this statement. So this is going to be x bar minus 1.96 sigma over root n, and x bar plus 1.96 sigma over root n. If you read the book, The Late Tasting Tea, they'll call this the confidence trick. This whole pivot thing, it looks like a statement about mu. It's a random statement about the endpoints. This is the hard thing that everybody has a hard time conceptualizing when they take Stat 101 and they say this is all very easy. Just do what I tell you and answer correctly and say it exactly right. They'll say that this is a procedure for constructing random intervals that cover the truth with some frequency. This is supposed to be 95. Usually just write equal and say it's 95. It's pretty close. So what does it mean? It means something different. It means I'm a statistician that has procedures and I'm able to give you intervals that will cover your answer. So you might say, hey, this is an interval that covers my answer, but there's a 5% chance it doesn't mean anything. It's not covering my answer, and my answer is somewhere else. So it's a statement about the procedure. So confidence interval are coverage statements about the procedure. So, i.e., what I mean is, for 95% of the data sets you give me under your collection method, you don't vary anything, I'll give you an interval that covers the truth. 5% of the time, I won't. 95% of the time, I'll give you a semi-meaningful answer. Nobody likes this. There's nobody I know that likes the confidence interval interpretation of things. Yet we've been indoctrinated with it and we use it. But what if I told you you can have both? I like these sort of procedures. I actually use confidence interpretations and I can build perfectly covering Bayesian interpretations to check to see if my code is right. So I run my code a whole bunch of times, I get this frequency interpretation of everything, and I come up with the optimal intervals to make sure that my code is converging correctly. And so I like these ideas. I really like it when I can be a Bayesian and come up with something that has optimal coverage properties. It turns out this interval, nobody argues with. We do teach that interval. Turns out to be a useful interval. They tell you never believe this interval is a statement about mu being in there. But if you're Bayesian under a flat prior, working with normal data, you can interpret it that way. That is what it is. Be aware, though, it's because of the symmetry of everything. The same basic shift nature of that parameter. So this gets really confusing early on because you're like, Bayesian, well, you just told me stuff I was doing before works. It's all right. I don't have to go do a retraction. That's good. Maybe I don't need this Bayesian class and I can keep doing what I want to do. Are you guys good with this right here? The difference between these things, this is a probability statement of mu and this is a probability statement about the endpoints. And in this example, it's exactly the same and that's satisfying. I could have built prior information in and pulled this interval around some mu naught and have like a mu naught shift in here with some weight. So I could influence it. That's kind of neat. I've got a lever in the Bayesian model, so I can give you something else if you want. I can steer. But they kind of seem the same. Do you like an example where they're totally different, or do you want to move on?
So just one thing, regarding the confidence interval, you're saying it's a probability statement about the endpoints. Is that also synonymous of saying that it's a probability statement about X bar?
Yeah, it's a probability statement about X bar. That's the only random bit in here. That's the thing that's inducing the randomness. Through Bayes' rule, by running through Bayes' theorem, I upgraded my mu to a random variable. And so now mu is random in my analysis. I used the randomness in the data to really drive at that. I use this probability rule to flip everything around. So right now this is just an idea that things are different. Would you like to see an example where things are just wildly different? Okay, let's do that. I was going to teach you about variance analysis, but let's do another example. I think it might be helpful. This one's pretty contrived to highlight the differences. This has been known to piss off many of my frequentist friends when I show them things like this. They have some response, I would never do that. You know? And it's like, well, the procedure says you could do it and make this mistake, how do you fix it? So it's a contrived example, but it pops up time and time again. I'll try to post a paper where this comes from. So, example. Confidence versus credibility. These are just words that human beings invoked. What does it mean to be confident? Confident about, and they distort this language, but what is confidence? It's this notion of a coverage set. Okay, so I'm going to change my language a little bit from interval to set. Okay, so I'm going to build something up around a set. So same thing, I can have a disconnected interval. That forms a set, right? Can't describe it as an interval. So I'm just going to change that language. Confidence, set, credible set. You'll see what I mean. So here's our model. So I'm going to say xi comes from no. Changing it. I have to remember this. This is going to be we observe either theta plus 1 or theta minus 1. I'll give you a heads up, I'm going to ask you to guess theta in a minute. Infer or learn. We observe either theta plus 1 or theta minus 1 each with probability ½ Okay, so this is a Bernoulli model, but it's a little different than what you're used to seeing. So I'm going to flip a coin. The side to the coin is either going to be this or that, each with probability ½ Okay, so this really is a Bernoulli realization, but I'm not telling you where this thing is centered. So if theta were 4, you'd either see a 3 or a 5, each with probability ½ And I'm going to let you see 2 random instances of this process. You get to observe. Two realizations. Two coin flips. So let me just write it out a little bit more mathematically. Your model is this. Probability of xi is going to be equal to theta plus 1. It's going to be equal to ½ The probability xi is equal to theta minus 1 is equal to ½ And if I were trying to soak up one more line, I would write probability of anything else is 0, but if I'm following Kolmogorov's rules, I've already added everything up. There'd be no negative probabilities in my model. And so that's what it is right here, and I'm going to say you're going to get to see observe x1 and x2. IID realizations from this process. Let me give you a confidence set. So here's a 75% confidence set. This is just a statement. And this is meant to be a very lousy answer. But what you can get by being the unconditional frequentist. So I'm going to write this down is Cx1, x2. So this just means confidence set. It's not an interval. It's going to have some conditions. So I'm going to give you either the average of the answers. So I'm going to give you x1 plus x2 over 2 if x1 is not equal to x2. Keep in mind what that answer will give you. Plug in x1 and x2, they're not the same. So I'm adding together theta 1, theta minus 1 plus theta plus 1. So I've got 2 theta, I divide by 2, it's theta. So I've given you a really good procedure right here if these two things are different from each other. Or I'll give you x1 plus 1 if these things are the same. I didn't get to see any variability in the data. The variability didn't help me. So variability is kind of a neat thing. It can help you to distinguish things, so we like some of it, but we don't like so much it's just so noisy. Variability is an inherently difficult thing to work around because you want some. You don't want to kill all your variability because it gives you the ability to predict. So here's a confidence set. I just want you to keep in mind this is 75%. Let me justify that. How often does this happen?
Half the time.
This happens 50% of the time. This also happens 50%. Why? I flip the coin, I get one number. What's the probability that I match it? 50%.
Yep.
So this is 50%. How often is this a good answer? If this happens, this is always a good answer. So this has 100% coverage. But it only happens 50% of the time. How often does this cover? If I gave you, if this happened to be a theta minus 1, I'm giving you the right answer. Or I give you an answer that's off by 2 units. So this is 50% coverage. Horrible answer. So this is kind of like what, now I would agree you can be a better frequentist than this if you condition on the right ancillary stat. Being the conditional frequentist is not an easy thing. So what's the right conditional ancillary stat? The difference of these two things, and you want to build a probability model with that included, and it turns out you can get a good answer. The problem with that is knowing how to do it. And so you need procedures that at least draw you in the right direction. This is a terrible answer. And so this means this. So as a 75% confidence set answer, I give either that answer, and I report with it 75%. I have a procedure that covers the truth 75% of the time. So if I keep running this, 2 instances, I check that, I look at how often I tag the truth. 2 instances, check that, see if I cover the truth, keep repeating it. How often would I be reporting back the truth with this answer? 75% of the time. So without conditioning on extra information in the data, you can give these stupid answers. That's not a good answer, right? Because what you really want to do is you want to say 100 or 50. Conditional on this, but you have to know how to operate as a conditional frequentist. Let me show you how to condition on data so that you're always conditioning on the right thing. Condition on your full data set. Bayesians do that. And so let's do the Bayesian analysis. So I don't like this answer, 75%. And if you said, I won't report that, I would report this as 100 or 50, I would ask you what your methodology is. So I'm an academic, so I want to know what paradigm are you following to do that? Is it just your intuition? This is meant to be intuitively so you can grasp is what's going on. But what about problems where you can't apply your intuition? Christina?
Why didn't x1 plus 1? Could you just write x1?
I did this arbitrarily. I could have also switched this to x1 minus 1 and gotten the same answer. So this was arbitrary in choice. But it gave me a 75% set. What I would also like to do is I'd like to kind of tell you the other 50% answer where it is, and that's what Christina's driving at. She's trying to think of how do I give you a good answer, and I'm sure all of us in this classroom could say, well, when I see this, I give this answer. If I see this, I give two answers, each of 50%. Question is what did you do to do that besides use your common sense? This answer is a 75% confidence set that doesn't make any sense. It's blurring over a process. Hypothetical things I've never even seen are giving me the 75%, and that is what most frequentists do. They're typical. I can give you a good frequency answer too. A 75% answer is Bayesian, and I'm going to condition on some of the data, and it's going to help me to do the right thing. So I need to write down the likelihood. So to be a Bayesian, we need a likelihood function. So a statement about theta, given the data, and a prior. Think about the process. You understand the properties of theta. My theta could be anything. I could give you anything on the real number line. Doesn't really change the nature of this problem. What prior would you pick? You're free to use your intuition without invoking real properties, and then I might fill in what you've done. Uniform. Same reason. This is a shift parameter, right? And so in our problem, this is a shift parameter. Just shifting the answers around, and I'm giving numbers off by 1 unit to the left or to the right. So it's a shift param. So I'm just going to say, let's use a prior that treats shift params invariantly. Same thing we did before. Okay, so we'll get more formal about this. If I want mathematical rules to derive priors, I will give you a mathematical rule to do this. We would have derived flat prior. You use the transformation invariant rule on this model, you will derive this. You don't have to just use your intuition. We'll get around to that later. Right now, a little bit of intuition. What's the likelihood function look like? So we need that. Likelihood of theta given x1 and x2. So in my class, if there's one thing you can come up with, it's the likelihood. You can always write it down. I give you the model, and write down and code up a likelihood. So Bayesians are always well practiced in writing down the likelihood function. So what's the likelihood function? Somebody help me out how you go about this.
It's a product of Bernoulli.
It's the product of?
Bernoulli.
Don't get it to me. So this is going to be fx1 given theta times fx2 given theta. Product of these two sampling things. I take the sampling model, what I just wrote down. So this model, boom and boom, and I'm done. So I just plug that stuff in, right? So how do I plug that in? What goes right here? Two pieces.
Both are piecewise functions.
Somebody help me out?
Both are piecewise.
Piecewise, can you? Do me the pleasure?
Sure.
Have a
So
look.
you'll have,
Give you some room.
I mean, so I'm just thinking to take this piecewise function and multiply them.
Let's do it.
Okay. So this would be probability is 0.5 for all pieces.
True.
X equals theta plus 1, 0.5, x1 equals theta minus 1. And just copy here with x2.
What is that function? How do I evaluate it?
So
What do I get?
So you get 0.5 at theta plus 1 and 0.5 at theta minus 1.
Oh, I put 0.5 and 0.5 and theta plus 1 and, right, I gotcha, yes. So he wants to write this down.
Yep.
He wants to write this down. He wants the function to look like this. This is going to be theta minus 1 and then theta plus 1. If these two things are separate, if x1, well, this is equal to x2, right here, he wants this function right here. And there was that x1 is theta plus 1, xi is theta plus 1. How do I get this right? But he's on the right track.
Yeah.
And so
So maybe I could do theta plus 2 times the Bernoulli.
times a Bernoulli, yeah, so maybe that. Give it a shot.
So this would
Think
be
about this process and encode it right.
plus 2 times 0.5 to the x1 times. Okay.
Yeah, you want me to save you? I appreciate the
I'll
effort.
write it larger. Times 1/2 x1 times 1/2 2 minus x1, I think.
It's an 8.
So this would be, oh, never mind. This would be and then plus some shift and scale.
Yeah, right. So shift and scale, that's the whole thing. But yeah, you got it. It's hard, right? So let me try it for a moment. Thank you for the demonstration. I want us to just go back to the problem at hand. You can think of it. I'm going to ask you all to do it. We're a bit out of time. We've got 3 more minutes, and I could write down the answer for you. But why don't you all think about this? This is the whole process. This is the connection between the data and the parameter. We know something about these functions. It adds up. It's a Bernoulli model, but it's a little bit different than the Bernoulli models we usually write down, because my parameter lives in the instance. So it's not P is sitting in there. If I give you Bernoulli data, it's a 1 or a 0, with P being the driving parameter, you could write down that likelihood. This is almost that, but it's different. And so a common mistake is to do this. This is what I usually see, so good for you for at least thinking about all the relationships between the x's and theta. That's good. I sometimes see people do this, 1/2, 1/2. I just multiply these two things together, right? And I've seen this answer probably out of a quarter of each one of my classes when I just ask them to do this. And you know this is the wrong answer. Why? There's no parameter in there. This is a parametric model. So if you write down a likelihood and it doesn't have your parameters in there, it's not your likelihood function. It's not what generated your data. So getting this right is of critical importance. Let's come back next time. I'm going to ask you guys again, what is the likelihood? It's not this. We had avenues of thinking to try to get this right, but let's just go back to first principles. So come back next time. I'll call on 1 or 2 of you and we'll see if we can collaborate and get this likelihood function. If we write it down correctly, we will get the answers that we want. So this thing will happen where it identifies with 50% and 50% probability where those two things are, or it puts all the probability at the right place. So the likelihood kind of has all the information. Come back, we'll finish this analysis, and then we'll move back to the normal thing and talk about variance. Also, we'll be doing a couple review sessions. So, Sierra, what time are those? What are the 2 dates?
Wednesday, Thursday, 6:30.
Wednesday and Thursday at 6:30. You want to do the first one and I'll do the second one?
I have coaching Wednesday.
Okay, I'll do Wednesday and Sierra will do Thursday. So they'll be about an hour apiece. Here. Thanks, you guys.